All right, today we're tackling something huge, Maxwell's equations. But I want you to think of them less as math and more like the fundamental language of the universe.
I mean, have you ever really stopped to think about it? How does your Wi-Fi just pass straight through solid walls? Or how does a microwave heat up your food with, no fire, no visible heat source? It feels like actual magic, right? Well, it's not.
The answer to all of it is written in a language that's older than humanity itself. And the most incredible part? It's described in just 4 stunningly elegant sentences. And today, we're going to learn how to read it together.
Okay, so every language needs an alphabet, right? Well, for us, that alphabet is all about electric and magnetic fields.
The most important thing to get is that this whole story starts with one thing: electric charge. So if you have a charge just sitting there, not moving, it creates an electric field. We'll call that E. Now, what if you get that charge moving at a nice steady speed, like a current in a wire? Well, then you get a magnetic field, which we'll call B. But here is where it gets really cool. If you accelerate that charge, speed it up, slow it down, make it wiggle, something amazing happens. It sends out a ripple, a combined electromagnetic wave. And just like that, you've met our 2 main letters, E and B.
Now look, this understanding didn't just pop into existence. It was kind of like a giant puzzle, assembled piece by piece over decades. You had folks like Coulomb, Ørsted, and the legendary Michael Faraday. They each found a critical piece. But it was James Clerk Maxwell who finally stepped back, saw how all the pieces fit, and put the whole glorious picture together.
And you gotta love the story of Faraday. This guy was a bookbinder's apprentice. He had very little formal education, but he understood all this stuff through pure intuition and just messing around with experiments. It just goes to show, if he could grasp these ideas without all the fancy math, we can too. They really are intuitive at their core.
All right, so we've got our alphabet, E and B. Perfect. Now we need some grammar. The rules that tell us how these fields actually behave.
And it turns out we really only need 2 main verbs to describe everything: divergence and curl. Divergence is just what it sounds like, a field spreading out from a point. Think of water spraying out of a fountain. That's divergence. And curl? Well, that's a field swirling around an axis. Picture water going down a drain. So you have spreading out and swirling around. That's basically the whole grammar book.
So, to apply this grammar, we use this little mathematical tool called the del operator. Honestly, the best way to think about it is like a universal translator. It's the symbol we use to ask any field a simple question. Hey, are you spreading out or are you swirling around?
Okay, we have our alphabet, we have our grammar. It is time to read our very first sentence. This is Gauss's law for electricity.
Now, the math on the left might look a little intimidating. Ignore it for a sec and just look at the translation. Our universal translator, that del operator, is asking the electric field E about its divergence. It's spreading out. And the equation gives us a clear answer. The spread is caused by charge. To put it even more simply, electric fields have a source. They start on positive charges and spread out from there. They have a definitive beginning. See? Not so bad, right?
So let's move on to sentence number 2. Now this one looks almost the same, but there's one tiny change that makes a world of difference. This is Gauss's law for magnetism.
This time we ask the magnetic field B about its divergence. We ask, hey, are you spreading out from a source? And the answer the universe gives us is 0. Always 0. Nothing. There is no spread.
So what in the world does that mean? It means magnetic fields don't have a starting point, they never flow from somewhere. Instead, they always form complete, closed loops. This one little equation is the reason you can't have a magnetic monopole. You can never ever find a north pole all by itself without a south pole attached. They just don't exist.
Okay, so those first 2 sentences were about static, unchanging fields. But the next 2, this is where things get really exciting. This is all about change. This is where the magic really happens. Let's dive into sentence number 3, Faraday's law.
This time, we're asking the electric field about its curl. It's swirling around. And the answer is just incredible. A swirling electric field is created whenever you have a magnetic field that is changing over time. And this isn't just some abstract idea. This is literally the engine that powers our entire modern world. Every single electric generator, from a giant dam to a power plant, works by using a changing magnetic field to create a swirling electric field. That is how we get power to our homes.
And that brings us to the grand finale, the last sentence, the one that ties it all together into a perfect, complete picture. This is the Ampere-Maxwell law.
This law tells us that a swirling magnetic field is created by two things. One, an electric current. People already knew that part. But the second part, this was Maxwell's stroke of pure genius. He realized a swirling magnetic field is also created by a changing electric field. Do you see the beautiful symmetry? A changing B field makes a swirling E field, and a changing E field makes a swirling B field. They're locked in a cosmic dance, creating each other.
And there they are. All 4 sentences. Together, this is it. The complete story of electricity, magnetism, and how they interact and dance with each other across the entire universe.
Maxwell immediately realized the mind-blowing implication. A changing electric field creates a swirling magnetic field, which, because it's also changing, creates a new swirling electric field, which creates a new magnetic field, and on and on and on. It's a chain reaction, a self-sustaining wave that just keeps going, propagating forever, even through the total emptiness of space.
So he asked himself, okay, if this wave is real, how fast does it go? He took the fundamental constants from his equations, numbers that came from simple lab experiments with electricity and magnetism, and he calculated the speed of this wave. The number that popped out was 299,792,458 meters per second. And that number was identical to the measured speed of light. Can you even imagine that moment? With just a pen and paper, Maxwell had discovered the true nature of light. Light is an electromagnetic wave. In that instant, he unified electricity, magnetism, and optics into a single, breathtakingly complete theory. And this leaves us with one final, incredible thought. If the visible light our eyes evolved to see is just one tiny sliver of this electromagnetic spectrum, what else is out there? What other invisible messages, what radio waves, microwaves, X-rays are flying all around us and right through us at this very second?